In this next morsel, we're going to talk about two components that are very much interconnected to one another. The first being the motherboard, and then we'll move on to addressing the CPU. The motherboard is probably best described as the body of a computer. Much like a human body holds all the organs together, a motherboard holds all the internal components of the computer together. The motherboard is much more than just a base plate for all the components to be slotted in. It also connects all the various components together, allowing them to communicate with one another where necessary. This communication between the components is achieved by what is called a bus. For example, the memory uses a memory bus, the CPU will use a frontside bus, the disk drives might use a SATA bus, and so on. But it doesn't stop there for the motherboard. It also provides power to all the other internal components. Without this power from the motherboard, the RAM, the CPU, the disk drives, etc. wouldn't be able to operate. They all have very specific and different needs for power, and the motherboard will regulate all of that and arbitrate it for all the devices. Motherboards conform to a physical standard called a form factor to ensure that there is component compatibility. As I mentioned in a previous morsel with the rack and tower chassis considerations, you need to ensure that the motherboard form factor that you select suits your needs. An analogy for the different form factor sizes for the motherboards might be extra large, large, medium, and small. Obviously, there are pros and there are cons for the variously sized motherboards, but you should always be aware of the form factor of the motherboard that you're selecting when designing your system. Smaller form factors may not accommodate multiple sockets for CPUs, whereas larger form factors will more likely be able to accommodate multiple sockets for CPUs, as well as more DIMM slots for RAM. They might even be able to accommodate more peripheral devices, but they come at the expense of needing greater power consumption and perhaps a larger chassis. So the form factor of a motherboard will be one consideration that you'll need to factor in when designing your system. Since the motherboard might be considered as the body of the computer, the CPU, or central processing unit, would then be considered the brain of the computer. A CPU executes instructions to perform simple operations, and as we've discussed in an earlier chapter, modern CPUs can perform billions of operations per second. To improve CPU performance and efficiency, they also possess a small amount of local storage, which is called cache, for instructions and operands. The CPU's very basic operational model is to take data from memory, store it in registers, perform some operations, and then send that data back to memory. There's obviously a lot more involved in this with incredibly sophisticated engineering and optimizations such as multi-stage pipelining, out-of-order execution, branch prediction, cache coherence, and so on. But this falls outside the scope of an introductory chapter. But for anyone that might be interested in finding out more about these concepts, I strongly recommend Georgia Tech's CS6290 High Performance Computer Architecture course that is available on YouTube and Udacity. Just be aware that it's a subset of a graduate level course offered for a Master's in Computer Science, so it can get very intense, but it's also very interesting and very informative. While the CPU is the most important component of a computer system, it's also the least understood by most of its users. Considering that it comes from sand, it's also getting the least amount of appreciation. Silicon is separated from raw sand and is purified to semiconductor manufacturing quality, which is called electronic-grade silicon. It's so pure that we're talking 1 alien atom for every 1 billion silicon atoms. Once that's done, the silicon is melted and a monocrystal is grown called an ingot. We end up with a 100 kilogram silicon ingot with nearly 100% purity. That ingot is sliced into individual silicon discs called wafers. These ingots sometimes are around 1.5 meters tall, and they're sliced into wafers that are around 30 centimeters in diameter. The wafers are then polished until they are flawless, mirror-smooth surfaces. Then a photoresistant finish is applied, which is the blue liquid in this picture. The wafer is spinning during this phase to get an even distribution of the coating. After that, UV light is applied, and it triggers a chemical reaction. There are circuit masks that block the UV light from areas of the wafer, thus creating the circuit pattern that we want. The middle item in this picture is a lens that shrinks the image to a small focal print. You can see it's about 1/4 the size of the original. There are some other intermediate steps and quality tests that are applied after this step until you end up with a wafer ready to slice. And then it goes through a few more steps and tests, and it finally ends up being packaged and sent out to market. See? What did I tell you? A very underappreciated piece of technology that starts from sand and ends up powering all our modern technology that we use today. CPUs come in many sizes, with two of the main CPU manufacturers being Intel and AMD, although many other CPUs also occupy the top 500, from manufacturers like IBM, which makes PowerPC, Fujitsu, which focuses on SPARC 64 CPUs, and ARM, which is a CPU that powers most mobile phones and devices today. As we've seen, a CPU is manufactured through photolithography, where shining light in certain regions of silicon produce certain patterns, which, when combined with other techniques like etching, build the structures that carry out certain functions. That process ends up with something that looks like this, which consists of various regions laid out on the CPU, such as the memory controller, the CPU cores, the CPU level 3 cache, and so on. Now, going back to that memory wall issue that I described in an earlier chapter, as CPUs continued to become faster following Moore's law, memory didn't quite keep up with that pace, so memory itself became a distinct bottleneck for CPU performance, as the CPU now had to wait for data to be fetched from memory and then sent to the CPU. Even today, memory access is a costly exercise. To make data crunching more efficient, CPUs now have very fast caches that are located on the CPUs themselves. While this is extremely beneficial for performance, it is also a very expensive commodity, so there is a trade-off between large cache and fast cache. Without discussing the way that caches actually manage their data through policies, associativity, coherence protocols, and so on, it's sufficient to know that it is a very complicated and in-depth technology without any singular standard approach. As with many things in computers, there are pros and cons to every application. But the basic principle of a cache is that the larger it is, the more data it can hold close to the CPU, but the larger the search space is at the same time for the CPU to look for the data it needs. That means it will take longer to search for the data in a larger cache. For this reason, CPU manufacturers have designed multiple layers of cache for a CPU. Level 1 is the smallest, but it's also the fastest. If there's a cache hit, which means that it's found the data it's looking for in the cache, it's not going to delay the CPU significantly because it's the closest to the CPU core itself. But if there's a cache miss, the CPU then has to look at the next fastest cache, which in this diagram would be the level 2 cache. That is a slightly larger cache than level 1, but it's further away. Because it's larger, it'll take longer to search for the data, so there's a higher latency. If it's not in level 2, it then moves up to level 3 and so on, until it eventually exhausts all the available CPU caches and moves on to the external memory, which is by far the slowest memory to access. And of course, if the data is not even residing in external memory, it will then have to query the disk drive to read the data off, store it in memory, and then send it down to the CPU. Traditionally, level 1 cache will be exclusive to a single processing element or a single processing core, while level 2 may or may not be shared across a few cores. Level 3 will be shared across all the cores of a single CPU. CPU cache technology is an extremely vibrant and interesting topic, and in my opinion, it is also a topic that every budding high-performance computing guru should be familiar with. When shopping around for a CPU, you'll be presented with an onslaught of information. But the most important aspects of a CPU that require attention for you will be the clock speed, the core count, and the memory bandwidth. In this example, this CPU is a 2.3 GHz CPU. That means one CPU core can perform up to 2.3 billion instructions per second. The core count in the CPU is 12, while the thread count is 24. Threads represent independent operations that can be staged for a CPU to execute, but the cores represent the actual available CPU processing element available to execute instructions at that moment. Having more threads to operate on than a CPU has cores available is referred to as symmetric multithreading, or sometimes known as SMT or hyperthreading. At this stage, for you, it's sufficient to ignore the thread count and just focus on the core count of a CPU spec. We will discuss hyperthreading in a later chapter. The memory bandwidth will reflect what RAM works with the CPU and how fast it can perform its operations. All the other information that's here isn't included just for giggles. It's actually all meaningful information, but for now, you should concentrate only on the core count, the CPU clock speed, and the memory bandwidth.